So we were working with a monoterpene, that is a molecule that contains two isoprene units. And we started with this linear precursor, which we got from head to tail connection of two isoprene units. And I showed you last time how you can get that from two smaller precursors. And then we talked about how to use basic reactions you've learned so far to get a very complicated but small natural product called alpha-pinene that has a 6-membered ring fused and sharing two sides with a 4-membered ring. And we went through, actually first, the synthesis of a related compound, limonene. We noticed that you needed a cis double bond in the ring, and yet in the precursor, both of the pi bonds are trans. And so to set up that situation where we can create a new sigma bond between carbon 4 of the blue subunit and carbon 5 of the pink subunit, we had to do a little isomerization, which is a quick SN1 type leaving group leaves to give a resonance stabilized carbocation intermediate. And if the leaving group comes back on tertiary carbon pink 2, that makes it so that the bond between 2 and 4 is a single bond now, not a double bond, which allows for free rotation. And if the leaving group leaves whilst the molecule is in this conformation, then carbon 5 is close to carbon 4, and you can do the attack of blue carbon 4 on pink carbon 5 to create a 6-membered ring. Notice this reaction is just a reaction from 351 that is pi bond attacks an electrophile. And the regioselectivity there is governed by what you learned in 351 is the Markovnikov rule. That is, you're going to make the bond between the electrophile and the less substituted carbon so that the more substituted carbon can have, number 2, blue 2, can have the positive charge. All right? As we've been, and then we saw that it's just a simple E1 elimination to get to limonene, where you remove a proton that's beta to that positive charge. As we looked towards the more complicated alpha-pinene, we found a bond that we made in the synthesis of limonene, that is the bond between 4 and 5. We found a bond between blue 5 and pink 1 that came from the linear precursor. But there was this additional bond between pink 1 and blue 2 that we had not made yet, and so we needed to figure out how to make that. One simple solution is to have the pi electrons, and there's some stereochemical issues that we're ignoring here. Carbon blue 4 is a stereocenter. The configuration of that stereocenter is going to be governed by the enzyme that catalyzes this cyclization process indicated here. But if we ignore stereochemistry and then flip the molecule over, that creates the situation where we can make the bond. Pi bond attacks the carbon 2. Now we talked about which of those two carbons should get the bond, and again, the regioselectivity is going to be governed by that Markovnikov rule. You want to get the more stable carbocation as the product. All right, so sometimes when drawing an intramolecular reaction like this, it's easiest to draw the new bond without worrying too much about whether the length of the bond is reasonable, at least in your drawing. So I'm going to continue to highlight the subunits here. Here are the two new bonds that we have made. I'll continue to label things 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Oops, now instead of a pi bond between 1 and 2, I've now made a new bond between pink 1 and 2. I've now made a new bond between pink 1 and blue 2. I'm going to try to indicate that. Not doing a particularly good job. Okay. Gross, huh? But have we got the right connectivity? And we need a positive charge on carbon 2. All right, yeah, and the question is, if we got the right connectivity, looking at our alpha pinene product, we need a bond between pink 5 and blue 4. We've got that. We need a bond between pink 1 and blue 5. We've got that. And then we need a bond between pink 1 and blue 2. And at this stage, if we want, we can try to draw things out in a slightly more reasonable shape. But let's try to highlight I'm going to remove the colorful highlighting between isoprene subunits. And I'm going to bring the drawing of alpha pinene from this perspective over here. Let's see, in purple, let's do the 6-membered ring. 1, 2, we maybe need a smaller font there. 1, 2, 3, 4, 5, 6, that's terrible. All right, there's the 6-membered ring. Now let's do the 4-membered ring in orange. 1, 2, 3, 4. That's here. 1, 2, 3, and then 4. So we've got all the connectivity issues right, and in fact, at this point, if we wanted to, we can redraw the molecule. Like that. So all that's left to completing and making alpha pinene is an E1 style elimination reaction where we remove this proton. And that gets us here. All right. Any questions you want to ask about that? Yeah, go ahead.
Yeah, so just, is it because of the Markov rule that it's acts on carbon 1 and carbon 2 with my 1?
That's right.
Yeah.
Right, the new bond that we make, which is here between pink 1 and blue 2, that's governed by the Markov-Nikov rule, so that the positive charge could be on the more substituted carbon. Yep, that's what those branching methyl groups are for. You know, if you want to ask why did nature choose that, it makes a lot of sense because it gives you some selectivity in all those pi bond additions. Okay, what else? Yeah. Uh-huh. Sometimes you've got to do methyl shifts and hydride shifts, and how can you tell when that's the case? You do your best. So I can show you an example of that. It's actually, I think, well, maybe an exam question from 351. Before I do that, let me just point out that this carbocation is a precursor to many different molecules. We've just shown 2, limonene and alpha pinene. But we can take that same precursor And if instead of doing that elimination reaction or the pi bond between 2 and 4 attacks the carbonyl carbon, or I'm sorry, attacks the positively charged carbon. Let me show you related product. This is called alpha thugene. And if you're kind of looks like a duck. So, sorry, lame. You can identify the same isoprene units in alpha thugene, but the connectivity you'll see requires a carbocation rearrangement. So one clue actually that I should have mentioned is notice that in the linear precursor, the tail has 2 methyl groups on it. You can always identify the carbon that used to be the tail of the linear precursor by looking for the carbon that's got 2 methyl groups on it. That sort of gives you your starting point. So if I look, and all of these products have it, right? In limonene, here is the carbon that has the 2 methyl groups, what used to be a methyl group attached to it. In alpha pinene, here is the carbon that has the 2 methyl groups. For thugene, here is the carbon with the 2 methyl groups. And so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I maybe could have gone the other way around and maybe should have done. Let's see. As I said, sometimes in identifying isoprene units, you will see multiple ways you could string the 2 of them together. In either case, you're going to get a proposed biosynthesis that's reasonable. And often the difference between those 2 is just going to be a matter of which enantiomer you get, which we are not caring about. So if I identify the subunits like this, 1, 2, 3, 4, 5, versus 1, 2, 3, 4, and 5. Here are the new bonds I made. Let's compare that with what we've got in our carbocation precursor. This isn't important, but I might call it this. This is called the alpha terpinyl carbocation because it's the immediate precursor to alpha pinene. In any case, we can sort of check off in the product here, alpha thugene, the bonds that are already in the alpha terpinyl carbocation, bond between pink 1 and blue 4, bond between blue 4 and pink 5. The new one, though, is the bond between 4 and 4. Okay? Now, as I look at that, pink 4 and blue 4, I got a problem, and that is 4 isn't a carbocation. Now, the way I typically make bonds, sigma bonds, in terpene synthesis is pi bond attacks carbocation, but I haven't got the carbocation in the right place. So, what could I do to get that carbocation in the right place? A carbocation rearrangement, your favorite, right? On that carbon 4, blue 4, you've got a CH bond that can line up with the empty p orbital on carbon 2, lean over and do a carbocation rearrangement. Now, you were taught maybe from me in 351 that we're going to worry about carbocation rearrangements, at least predicting them, when you can rearrange a less stable carbocation into a more stable carbocation. And that situation was when, say, a tertiary carbocation is adjacent to a secondary carbocation is adjacent to a tertiary or a quaternary carbon. And that's still true. That's the situations where I want you to be able to predict that it would happen. But this is a different situation. This is a mechanism question, and we're trying to figure out, given that something happened, how does it happen? And in that case, it's perfectly fine to rearrange a stable tertiary carbocation into a similarly stable other tertiary carbocation. That's a 1,2 hydride shift. I wouldn't have asked you to predict whether or not that would happen, but given the observation that it does, could you figure out, or given an observation, could you figure out that it was necessary in order to get the right connectivity? That's the kind of thing that I'd expect you to be able to do. In other words, you didn't have to predict that it would happen. The connectivity in the product tells you that it must have happened. Then that puts the positive charge on blue 4. Oops. Then we're going to have a simple pi bond attacks carbocation, again governed by Markovnikov regioselectivity. The new bond we make is going to be between pink 4 and blue 4, so that the positive charge can be on pink 2, where it is more stable. And that's kind of cute, because now it looks like the duck has eyes. And then getting the final product is a simple case of E1 style elimination to give you your new pi bond. All right, so that's an example of a carbocation rearrangement. Again, you're not predicting whether it would happen, but given a result, can you figure out that it was necessary? All right, questions about that? Okay, so without that same combination of basic steps, right? Leaving group leaves, get a resonance stabilized carbocation, pi bond attacks a carbocation, carbocation rearrangement, and finally elimination. There is a bewildering array of complicated molecules that you can make. We're going to increase in complexity a little bit, and I'm also going to show you something you've likely seen before from 351, and that is how to get a steroid precursor from a similar sort of starting material. All right, so get ready to draw something horrible. But the reason I'm pushing you on this, 2 reasons. First, the essential oil industry is big in Utah, and a lot of these are essential oils. I don't recommend that you purchase essential oils with the desire to cure yourself of various ailments. The industry is not regulated, and they're not allowed to do health claims that the FDA would need to verify. If you want something that's effective, you need a double-blind, controlled, randomized clinical trial. That being said, the placebo effect is powerful, so should you choose to take advantage of it, just do not pay a lot of money for it, is my recommendation, okay? And that being said, you can isolate natural products from nature with interesting chemical properties. And there's a huge field in organic chemistry that's related to finding strange natural products, testing their ability to kill cancer cells or bacteria or fungus, and a lot of people are interested in this. So the idea that natural compounds might have interesting properties is is useful and important. Again, you just want to be skeptical in evaluating health claims. All right, so I'm going to draw a molecule here that is isolated from the cedar tree. It's called cedarol, so it's an alcohol that you can get from cedar. Dun, dun, dun. You hate it already. There's 2 5-membered rings and a mysterious 6-membered ring that we have to draw kind of funny. And I will say that you get this from the following linear precursor, which is called farnesyl pyrophosphate. This is the extended version of geranyl pyrophosphate. It's got 1 more isoprene unit in it than does geranyl pyrophosphate, with the pyrophosphate leaving group. 3 isoprene units linked together head to tail. And we can number them if you want. So your first task is identify the isoprene units in cedarol. And because I tell you that it came from this linear precursor, I want you to see if you can find a way to assign isoprene units that string in cedarol that strings 3 isoprene units together in head to tail fashion. And I'll give you a hint. Start with the dimethyl tail, the fish tail. All right, so I'm not going to do it for you. Take a minute, figure it out. I won't always be with you late at night when you're asking yourself, where are the isoprene units in this natural product? Don't tell me that hasn't happened to you before. No, I don't want you to, we're going to do that together. What I want you to do is identify in cedarol what the isoprene units are. No, yeah. Bored yet, or are you still working? Okay. least by my looking at this, I think there's probably two ways to do this. Both of them are fine. So if you've got one, call it, it works, call it good. You don't need to find the second way. All right. So starting from these two, I told you start with the dimethyl tail. And that is the starting point. Okay. So where am I going to go next? There are two carbons connected to carbon. Well, let's see. If that's the dimethyl tail, then we can number blue 1, 2, and 3. There are two carbons connected to blue 2. Which one do I want to go to for the next carbon in the isoprene unit if I want to wrap a single head to tail chain of isoprene units around the molecule? A la izquierda, right? What a great word, by the way. Isn't that a great word in Spanish for left? Izquierda? I don't know what that means. Okay. The problem with going the other way is that I could go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, but then I'm over here and I've got this disconnected isoprene chain. And there are some natural products like that, but I'm telling you there's a way to do that where you take a single chain of isoprene units and wrap it around the whole molecule. So then where? Now I'll call this blue 4. Which one's blue 5? I could go here to the up or here to the left. Left makes more sense because then this could be one of the next isoprene unit and the branching methyl group's in the right spot. Okay, that's good. That would make this the bond between isoprene units blue and pink. So this would be pink 1, 1, 2, branching methyl group on 3. So that provides some comfort. That lets us know we're in the right spot. This one would have to be 4. Here's where you got some flexibility. Which way should I go? Yeah, it works out either way, right? If I go here and call this 5, then this would be the bond between the two isoprene subunits, and I could go 1, 2, 3, 4, and 5. That works. Alternatively, I could call this one 5. That would make this the bond between two isoprene units. And this would be 1, 2, 3, 4, and 5. And I don't really have a great solution for you in terms of which is better. So I think the answer we're going to stick with is that you pick one and see if you can draw the mechanism. And if you can't, then maybe there was a better way. I'm going to choose the first of those options that I showed you, and I'm going to draw a mechanism based on that. I don't, because all of this is going to be multiple choice, I'll try to point out for you the format that this question could be in. And if you want to try to draw, after you've seen what we're going to draw now, if you want to try to draw a mechanism for the other arrangement, you can certainly do so. In terms of how could you tell which one is right, that's the realm of like empirical biological experiments. So let's choose that. 1, 2, 3, 4, 5. Here's a new bond that we made. 1, 2, 3, 4, 5. Here's the bond between pink and orange, and then 1, 2, 3, 4, 5. Now, What I have done previously when putting questions like this on an exam is I will identify all of the new bonds that were made in this process of making cedarol, that is all the new carbon-carbon bonds, and I'll even identify the isoprene units for you, but then I will ask this question: which bonds of the ones that are in red, and you could call them A, B, C, and D, or give them some other designation, which bonds were present in the linear precursor versus which bonds had to have been made by cyclizing that linear precursor? Now that sounds hard, but it's actually a really easy question. What are the bonds in the linear precursor? What are the sigma bonds in the linear precursor? The 5 ones, right? Anything else you had to make. Okay, I feel like I just gave you an answer. Like that was 10 points free. It's not this molecule on the exam, but it's a similar situation. And I basically just gave you those 10 points free, so you're welcome. Okay. Questions so far? What medicinal properties does this?
Does it cure cancer, or does it just do that?
I think it probably just smells like cedar. Cedarol, essential oils of conifers, including junipers and others. It's related. Let's see, blah blah blah. It makes up about 19% of cedar wood oil from Texas. I don't know why we care about Texas. Blah, blah, blah. This is Wikipedia, so who knows? This is fun. Results of a 2015 study suggest that cedarol strongly attracts pregnant female mosquitoes after they have fed.
So why not do something like
What's the point of that?
That's right. You can use it to create baited traps so that the pregnant mosquitoes die before they, it has been shown to have antioxidant and anti-inflammatory effects, but that's an unreferenced statement, so I like to see the data. Something about antiseptic, anti-inflammatory, antispasmodic, astringent, diuretic, sedative, insecticidal, and antifungal activities in vitro. That's from a journal that I don't recognize. So, there's a Saturday Night Live sketch from the 80s or 90s advertising some kind of product that is both a floor cleaner and a floor shiner and a dessert topping, which sounds like you've got something like that here. I don't know. Anyway, it's pretty. So let's try to start teasing out how to think about a mechanism for this question. And the way a mechanism question on this subject would show up is I'm going to show you various mechanistic steps, some of which lead to the desired product and some of which don't. And you have to pick out the ones that are on the path, that give you the right connectivity. That's not as hard as it sounds either. You don't have to generate the mechanism from scratch like we're going to, but rather evaluate among various mechanistic steps which ones actually lead, are on the path and actually lead to the product. So to begin with, I'm going to suggest that as we go back and look at what we've done before, we know how to make 6-membered rings. So that's probably the best place to begin. Notice in making a 6-membered ring before, we know how to make the bond between 4 and 5 of adjacent isoprene subunits. If you look at cedarol and identify the 6-membered ring right here, one of those bonds is a 1,5 bond. That already exists. And actually, maybe I'll make a distinction. Maybe I will no, we don't want to use green. Red-green colorblind is a major issue to avoid in drawing. So I'm going to color in blue the bonds that are not ones present in the linear precursor. So we basically have to take care of those 3 bonds. Actually, that means the process is not as difficult as you thought. There's only 3 new bonds in this thing relative to the linear precursor. But what I want to say is, by analogy to what we did before, in that alpha terpinyl carbocation, we have a bond between 1 and 5 that's already present, and then the bond between blue 4 and pink 5. And we've sort of got one of those here, pink 4 and orange 5. So that gives us a clue as to how we're gonna make this, all right? So, looking at the linear precursor, if I want to make a bond between pink 4 and orange 5, what do you think has to happen? First thing is leaving group leaves, right? So I'm going to skip ahead a couple of steps because we've seen stuff like this before. We're basically going to do exactly all of this to make this 6-membered ring, only the precursor is going to be longer. So what if I redraw the molecule like this? And as I said, I'm going to skip ahead past a couple of steps. Do you remember we had to do some isomerization to get the double bond in the right configuration? All right, so here's the orange subunit, 1, 2, 3, 4, 5. Here's the pink subunit, and here's the blue subunit. I put the OPP in a different spot. Do you remember how before, to get the cis double bond, or to get carbon 5 close to carbon 4, we removed the leaving group. We had it come back on the tertiary carbon so we could rotate around the carbon-carbon bond. So I'm skipping over multiple steps to save us some time. What I'll do though is see above for pi bond isomerization. Okay, so we get to that point. The leaving group's going to leave. That generates the resonance stabilized carbocation. I'm going to draw one of those resonance structures. Whoa, not that one. To put the positive charge on that carbon. We'll color in our isoprene units. We'll use red for the bonds that we already have. I know it's tedious, but sometimes I think labeling carbons can help. As suggested by the popular Latter-day Saint song, count your carbons, name them one by one, and you'll be able to keep track of all the bonds that are done. I don't know, sorry. So, we're going to make that bond between 4 and 5 over here by the exact same step that we did previously, which is pi electrons attack electrophile to give us a new 6-membered ring, and the regioselectivity of that process is going to be governed by the Markovnikov rule. That is, we want to get the more substituted carbocation. So here is the new bond that we made, and I need to get rid of that pi bond and put a positive charge on pink carbon 2. All right. So far, that should look exactly like getting the alpha terpinyl carbocation in terms of mechanistic steps. And we have the added benefit that we have just made one of the bonds of the 3. So we're a third of the way there, which isn't as lyrical as halfway there in the famous Bon Jovi song. All right, so now let's look at what other bonds we have to make. We need a bond between pink 4 and blue 4. And we also need a bond between orange 4 and blue 2. So, what are we going to do? So, I'm going to make a recommendation. I want you to think about this strategically. Of the remaining bonds that we have to make, the one between orange 4 and blue 2, and then the one between pink 4 and blue 4, let's think about the order that this needs to happen in, okay? Right now, we have a positive charge on pink carbon 2. So first, it seems like I'm going to want to do something to get the positive charge on pink carbon 4. Right? I know that I need a bond between orange 4 and blue 2, but right now I haven't even got a positive charge on blue 2. Okay? You can sort of, based on the atoms that are involved in these bonds, you can sort of tell who was the electrophile and who was the nucleophile, right? As I look at this bond between orange 4 and blue 2, thinking backwards, it makes sense that if there had been who's the positive charge and who has the pi bond, probably the positive charge is on the more substituted carbon, blue 2. Probably the pi bond was between 2 and 4, right? All right, anyway, as I'm looking here, I need a bond between pink 4 and blue 4, and right now the positive charge isn't on blue 4. So maybe a carbocation rearrangement. You've done that before too. We've done this exact same thing actually when we went to make alpha thugene, and we saw connectivity that we could only explain through a carbocation rearrangement. So let's go ahead and do that. Let's and see. And sometimes when you're testing out these mechanisms, you got to try something, see if it gets you something that you can get the right connectivity. And if it doesn't, you got to cross it out, erase it, and go back. So don't be afraid to try things without knowing beforehand how it's going to turn out. Man, there's gospel applications flying off the page today. Okay, so that puts our positive charge on carbon 4. Now, how would I make, if I need to make a new bond between blue 4 and pink 4, am I set up to do that now? How would that work? what kind of step happens there? Pi electrons attack, positive charge. Who gets the new bond? 4, so that the positive charge can be on 2. Good. Let's, now this is an intramolecular cyclization reaction, and those are painful because you have to keep track of carbons. Fortunately, we are good now at counting our many carbons. So, though we're going to have to redraw the molecule now in a slightly different shape. Let's first, if we're going to make a bond between this 4 and that 4, let's see what size the ring is. 1, 2, 3, 4, 5. Oh, okay, that's not so bad. Okay. By the way, if you want to bring, you know, colored pencils and highlighters to the exam, that's fine. You don't have to draw anything if you don't want to on a multiple choice exam. But if color is helpful to you in sort of keeping track of this, that's fine. All right, what I'm going to do now is 4 is now involved in, pink 4 is now involved in a 5-membered ring with blue 4. And so I need to draw a 5-membered ring right here. And then I'm going to number 5, 4, 2, branching methyl group 3. Does your brain hurt at all? Mine kind of does. Is that right? There's the bond between pink 1 and blue 5. This is blue 4. We're using this color for the new bond that we made. Blue 4 should be connected to blue 2, which should now have a positive charge on it. Yikes. Okay. That kind of looks like a friendly, I don't know, something or other, stretched out kind of like this. Oh, friendly neighborhood Spider-Man, okay. Or an alien, I guess. I don't know. That's more. I like that. How do I redo that? Okay, that's good. Still strikes me as somewhat avian, like if we put a beak there, it's kind of a chicken. I don't know. All right. Okay, we're closer, right? Because now we've made 2 of the 3 bonds. We're 2/3 of the way there. Okay. So now are we set up? Let's see whether we're set up for anything or for the right connectivity or whether we need a carbocation rearrangement. Our next bond that we need to make is between orange 4 and, orange. I'm confused. Orange 4 and blue 2. Oh, actually, pi bond and the positive charge is in the right spot, right? It's almost like somebody planned it to be this way. The connectivity of the molecule and those branching methyl groups build in the pi bonds at the right intervals to make 5- and 6-membered rings with Markovnikov addition, and which is why you can get such a wide range of beautiful natural products from that simple linear precursor. So Pi electrons attack. Again, let's see what size ring we just made. Between 4, 1, 2, 3, 4, 5. There's our other 5-membered ring. And this is where drawing it gets miserable. And I'm not sure what to tell you other than before you worry about drawing the miserable molecule, just draw it in the exact same way with a really long bond. All right, so that's going to be a bond here between 4, 1, 2, 3, 4, 5. With a positive charge on orange carbon 2, which is the more substituted carbon where it's more stable. All right. So now let's copy the Cedarol figure and see how close we are. We've now made each of those bonds. And with a little bit of work and staring at things for a while, you can see how we've got all the right connectivity here. What am I missing? Can you think of a way I could get that OH group there? Yeah, boring 351 reaction. Water attacks carbocation. And then you'd need to deprotonate the resulting oxonium ion to get the alcohol in the right place. Okay? The point, my friends, is that all of the connectivity here, and even the fact that the OH group ends up on that particular carbon, all of that's embedded in the structure of the starting material. Okay. Now, there are, of course, enzymes that guide this process, and so it's a terrible question for me to say, predict the product and give you farnesyl pyrophosphate, because there's a lot of things that come from that. That's not a good question. What is a good question is to say, first, of the bonds that are here, which ones were in the linear precursor? Let's see, it's also a good question to say, of the options here of mechanistic steps, which ones give you the right connectivity? And you haven't got a very long list of mechanistic steps. You've got carbocation rearrangement, you have leaving group leaves, you have pi bond attacks positive charge, you have elimination, and we just introduced a new one here, nucleophile like water attacks positive charge. But with that limited alphabet of mechanistic steps, yeah, can you pick the ones that lead to the right connectivity? So, at the end of your chapter, there are a ton of strange looking natural products. And even, let's see, this is in terpenes and terpenoids at the end of your chapter. Even if they don't ask you to draw the mechanism, it might be worth playing with some of these examples to see if you can come up with a mechanism that would lead to the products. Okay? All right. That's sort of it for terpenes, though I do want to walk you through the beautiful cyclization process that gives us cholesterol, or rather a steroid precursor. But let's take a break before we do that, and then we'll talk about nucleic acids too. Okay? So, you have on this portion of the molecule an electrophile, and you've got built into it nucleophiles. Now let's just sort of think about regioselectivity and sort of plan ahead. The epoxide gets protonated. Which carbon of the epoxide is most electrophilic when the epoxide is protonated? That's a 351 question. One, two, three, four, five. 2 or 4? 2. That is because for a protonated epoxide, the leaving group starts to leave, and it leaves preferentially from the more substituted carbon where a buildup of positive charge is more stable. All right, so I'm going to use, I don't know, a red circle for the electrophilic hotspot for this molecule. All right. Now, we've got a nucleophile. How many bonds away? Well, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Let's use a blue circle for what we think the nucleophile will be. You have a pi bond between 2 and 4. That can be a nucleophile. It could attack this electrophilic center. Of the 2 atoms that are involved in the pi bond, who's going to do the attacking and who gets the positive charge? 4 does the attacking. So I don't know why I'm choosing blue. Well, whatever. I'm indecisive. That's a big problem. All right. And when we do that, I hate that I'm using green because of color blindness. Let's use gray, I don't know, brown, sure. Gross. Purple, just egregious waste of classroom time on color schemes. When we do that, 2 will then be an electrophile. And then you've got another double bond that's here, right? So I'm going to attempt to draw for you, hopefully you're seeing what can happen here, which is that pi bond will attack the epoxide, opening it up. At the same time, I will have a new positive charge on carbon 2 such that this pi bond could attack carbon 2. And you're going to get a cascade of nucleophilic attack. So I'm redrawing this molecule in sort of a serpentine shape to try to give you a sense for how the process happens. And it's going to take me a minute, and I apologize. All right, so there's your epoxide. Here's going towards the back, away from us, is carbon 5, bonded to carbon 1 of the pink isoprene unit, 1, 2, 3, 4, 5. Now I'm going to try to draw the rest of the molecule. I know what's going to happen, so I'm going to try to draw all of this in a way that makes it a little bit clearer what happens. Whoa, sorry, I got too many carbons there somehow. That was right. Okay. I'm going to label the, oh shoot. Sorry, I messed up here. There should have been another carbon. I'm sorry, I recognize that's obnoxious. And you don't need to copy all of this down if you don't want to. You can get it in the notes. So enough with the frantic scrambling to write things down. And I'm sorry, I'm not drawing this better and more clearly. Okay. So those are our isoprene units. We're going to, in basically, and if you do the computational analysis on this, there's evidence that all of this sort of happens in the same step. You can draw it stepwise if it's helpful to see the intermediates. I'm not going to do that today. I'm going to show the pi bond attacking the more substituted carbon of the epoxide. At the same time, that would cause a buildup of positive charge on carbon 4, where it is more where the positive charge is more stable. So then we're going to have the pi bond between orange 2 and orange 4 attack pink carbon 4. I'm sorry. You're going to let me do that?
Yes.
You don't want to say anything. You're so embarrassed. I can name it however I want, right? Because I'm in charge.
Doesn't matter, I remember it.
1, 2, 3, 4, 5. Okay. I'm happier with that. Is that okay? You guys okay with that? Sorry about that mistake. The more substituted carbon 2 gets the positive charge. That will be the one that's attacked by the pi bond from the orange isoprene unit. Let's comment on ring size that we're making, by the way, as we're going through this. So we make a bond between pink 4 and blue 2. That's a 1, 2, 3, 4, 5, 6-membered ring. So we got that going for us. If we make a bond between orange 4 and pink 2, that's a 1, 2, 3, 4, 1, 2, 3, 4, 5, 6-membered ring. Okay. That's going to cause a buildup of, if we make the bond between orange 4 and pink 2, that's going to cause a buildup of partial positive charge on more substituted carbon 2, where it's more stable. Here's where we're going to do, and this is sort of governed by nature. Notice that we've got now, we're into the green isoprene subunit. We have an electrophile here at orange carbon 2. The pi bond between green 2 and 4 could attack orange carbon 2. Which one gets the bond? If it's 2, it's a 6-membered ring. If it's 4, it's a 5-membered ring. So you got a trade-off, right? You go one method, you get the more stable carbocation, but you get the smaller ring. You go the other side, you get a less stable carbocation, but you get a better ring. All steroids have a 6-membered ring at this position. So we're going to show pi electrons making a bond between green 2 and orange 2. That's a 6-membered ring, so that there would be a buildup of partial positive charge on carbon 4. And then we're positioned so that purple, the pi bond between purple 2 and 4 can attack green carbon 4 to make a 5-membered ring, leaving a positive charge on that more substituted carbon. So that's the cyclization process, happens all in one sort of concerted step. And again, it's interesting how you have the placement of these pi bonds in just the right places to make 6-membered rings. So let's draw what we've just done.
The final isoprene just stays as a tail.
The final isoprene just stays as a tail. Why doesn't it cyclize?
It would have been a 4.
I don't know. You could have cyclized it. It would give you a 1, 1, 2, 3. Yeah, I guess maybe it would have been a 4. 4 or 5. All right, so let's draw what we've made. Here's the chair. Now you begin to see why organic chemists care about chairs, because they're present in important natural products. I'm going to draw in red the new bonds that we made as part of this process. So there's one of them. I realize I'm not drawing a realistic chair for this next ring, and that's okay. Just to keep the visual connection between what we've just done. Sorry, temporarily confused. All right, I think I've got that. So here's our first isoprene subunit. Here's our next one. Here's our next one. Here's the green one. And I promise you in red are going to be the 4 bonds that we made in that process. All right, linear precursor to carbon skeleton that's elaborate. It might also help at this stage to try to redraw things out as though we were looking at the molecule from above. I think that might help us just a little bit. Okay. So, a lot of complexity built up in that original step. I'm dropping at this stage the labeling of the isoprene units and the new bonds that we made in red. But again, kind of crazy from a linear precursor to something that complicated in a single step. Now, what happens next, you're also going to hate because it is a cascade of carbocation rearrangements. Great. And this happens to get to, I'll show you the product. Well, no, we'll just do the cascade of carbocation rearrangements. At this point, you're going to be asking, why does it happen this way? What makes it happen this way? And I don't have a good answer for you. So I'm going to draw the final product, and then we'll talk about how to get there via carbocation rearrangement. However, this basic pattern of three 6-membered rings attached to a 5-membered ring is characteristic of a lot of different biological molecules that have diverse roles, including the steroid hormones, including cholesterol, including bile salts. Even vitamin D actually comes from this molecule as a precursor. All right, so if I compare the final product here, or rather the product that we're going to get and then sort of stop at, is called linosterol. If you look at it, it looks like everything's in the wrong place, right? This proton seems to end up somewhere else. This methyl group seems to end up here. This methyl group seems to end up there. And we have a double bond between these two carbons with nothing going on there. Basically, we need to find a way to move this positive charge all the way from here, outside the ring, to here. And we're going to do that through a series of carbocation rearrangements. So we can show that if this proton leans over and does a 1-2 shift, that would put a positive charge here. I'm not going to draw that intermediate. If then this proton did a 1-2 shift, that would move this proton to that carbon, leaving a positive charge there. Then this carbon leans over and does a 1-2 shift. Notice that the stereochemistry of the groups that shift doesn't change. This proton was down, it shifts over, it is still down. This methyl group was up, it shifts over, it is still up. Lastly, this methyl group can shift over, and that will get you to the precursor to linosterol, which has a positive charge on that carbon. You can ask at this stage, why on earth don't we just continue doing carbocation rearrangements? The answer is, I don't know. And people have done calculations on this process, and to some extent, it may be that this actually is the most stable carbocation, so you're just in an energy minimum and there's no driving force to do anything else. I can't tell you why that would be the case or ask you to predict it. But given the result of where the double bond is and where the other groups end up, you can tell that rearrangements happened. At this late stage then, all that's left is to remove a proton in an E1 type step adjacent to the pi bond. It is true there are other pi bonds, there are other beta protons that you might have removed. That's the one that nature chooses. If you want sort of a hand-wavy cop-out answer, you could say that the enzyme makes it go that way. But there is, from a simple linear precursor, a very complicated process, a very complicated molecule. We're not even close yet to cholesterol. There are 19 more steps, which we're not going to do. before you get to cholesterol. Some of this, if you look at the structure of cholesterol, some of this involves losing some methyl groups and some other things. But from cholesterol as a precursor, you get vitamin D, you get the steroid hormones, you get bile salts, all sorts of different metabolic products. All right. The question on all of your minds is, what exactly am I supposed to get from all of this? The answer is all of it. Every word I say is important. I'm a professor, for goodness sakes. I don't say things I think are unimportant. And you're paying to hear it, so just soak it all up, right? I'm teasing. I want you to understand the regioselectivity of this process. That is, regioselective epoxide opening under acidic conditions. You predicted that the more substituted carbon would be the one that got attacked, okay? That's straightforward. How about pi bond acting as the nucleophile to attack? What's the regioselectivity of that? In general, it's Markovnikov so that you get the positive charge intermediate on the more substituted carbon. What do I want you to know about carbocation rearrangement? Well, if you observe the fact that it has happened, can you explain how it happened via a series of 1-2 shifts? Okay, so anything else you want to ask about that? I think we've sort of beat that to death, but we can continue. Okay. All right, let's talk about nucleic acids. Some things you're going to memorize here in the same way that you memorized stuff from the amino acids. A lot of the nucleic acid stuff I'm going to leave for your biochemistry course in the future. But there's some interesting stories to tell that we'll spend just a little bit of time on. All right. So let's talk about the various pieces of nucleic acids. First, the heterocyclic base. A heterocycle is a ring that contains atoms other in addition to carbon. That is oxygen and or nitrogen. So you have two kinds of bases in nucleic acids. Some are called purines, the others are called pyrimidines. There's a whole world out there of organic chemists that like to flex by knowing the names of heterocycles. You've seen some of them before that I've used in passing. For example, I called that, I called this imidazole. That's a heterocycle name. I called this molecule before that you've seen pyridine. That's a heterocycle name. I called this one piperidine. That's also a heterocycle name. But they can get much more elaborate, and some organic chemists, as I said, really like to flex by knowing the names of complicated heterocycles. Like for example, isoxazoladinone. Doesn't that sound kind of funny? I can't actually draw it for you, or I could, but then I might get it wrong and be embarrassed. So in any case, even non-organic chemists have sort of picked up on purines versus pyrimidines because they have different shapes. So you'll hear those words in the future. I hear the word purine and I think of Purina dog chow, which used to be advertised back when people watched television and there were commercials. I don't know whether Purina dog chow is especially rich in purines or not. There's probably a connection. So the basic core structure of the purine is a 5-membered ring containing 2 nitrogens with a 6-membered ring containing 2 nitrogens. And then what's added to it determines whether it's one base versus another. The base I'm going to draw now is called adenine. The term adenine refers specifically to the base part of the nucleotide and not part of the other stuff. Adenine has an NH2 group at this particular carbon. There is a way of talking about positions on a purine ring. They do have characteristic numbers. I don't know what those numbers are off the top of my head, and we won't worry about them. This NH2 group is called an exocyclic amine, an exocyclic amino group, because it is outside the six-membered ring. Another thing to pay attention to as you look at these purine bases is groups that can be hydrogen bond donors versus groups that can be hydrogen bond acceptors. So H bond donors, let's give the color blue, and H bond acceptors, I'm sorry, I guess we should have highlighted the word donor. That is groups that have polar bonds between hydrogen and an electronegative atom where the hydrogen has a partial positive charge on it. That's a hydrogen bond donor. A hydrogen bond acceptor is an electronegative heteroatom that has a lone pair on it, and we will use the color red for acceptors. So hydrogen bond acceptors include these groups. The exocyclic amino group is aniline-like. You've got a lone pair on that amino group, but it's conjugated with the ring, and so it's not a very good hydrogen bond acceptor. However, the protons of that aniline group, and so I'm going to just erase the lone pair so we focus in on the donating ability of the hydrogen bond donating ability of those NH bonds. I'm writing down that the lone pair is conjugated. The purine ring is aromatic if you count the pi electrons, 2, 4, oops, and these two, they've got lone pairs on that nitrogen, so 2, 4, 6, 8, 10. So it's an aromatic ring. But notice that the lone pairs that I've said are hydrogen bond acceptors. Those are all in sp2 orbitals on sp2 hybridized nitrogens. They're orthogonal to the pi system. They can accept, they can participate in hydrogen bonds. Next, I'll show you the structure of guanine. These don't roll off my brain in the same way that the amino acids do, because I'm not a nucleic acid chemist. So, as with the other purine, adenine, guanine's got that same basic 5-membered ring with 2 nitrogens, 6-membered ring with 2 nitrogens. Oops. The difference with guanine is that you're going to have a carbonyl group here, and instead of a double bond between this carbon and the nitrogen, that nitrogen is going to be involved in an amide bond with a proton. And then there's going to be an exocyclic amino group. So I'm not actually going to draw the lone pairs that are on this nitrogen because they are tied up in resonance, conjugation, and aromaticity. What you've got with guanine then is a different pattern of hydrogen bond donors versus acceptors. You've got, in a place where with adenine you had a hydrogen bond acceptor, now you've got a hydrogen bond donor. Now you've got an acceptor, that carbonyl oxygen. Do you see exocyclic amine, carbonyl oxygen? That's a switch. In a place where you had this ring nitrogen that was a hydrogen bond acceptor, now you have a hydrogen bond donor. That's a switch. And then in a place where you didn't have anything for adenine, you now have an exocyclic amino group. You still have these two lone pairs on these two sp2 hybridized nitrogens that can be involved in hydrogen bonding. I will say that these groups here are the ones involved in Watson-Crick base pairing. And you can see that that pattern of donor, acceptor, acceptor, donor, donor is different for adenine versus guanine. And yeah. You've got the potential for 2 hydrogen bonds involving adenine versus 3 hydrogen bonds involving guanine. Okay. Questions so far? Bored to tears? I'm kind of bored. Sorry. Stuff to memorize. Okay. So pyrimidines are 6-membered rings. They're smaller than the purines. Their shape is different. Let's see. Dang it. All right, the squiggly line indicates where the base is attached to something else. I'm drawing for you here thymine. Thymine is only present in DNA. If we're in RNA, you lose the methyl group and you have uracil. The pattern of hydrogen bond donating versus accepting groups for thymine is you have a donor here, and you have an acceptor here and an acceptor there. And maybe if I rearrange some things. Oops, sorry. I'm just trying to show you how the exocyclic amino group on adenine can engage with a hydrogen bond. I'm showing them at way far too long distance with the oxygen, the carbonyl oxygen of thymine, and how the ring nitrogen of adenine can engage in a hydrogen bond with this NH group on thymine. Notice that this oxygen on thymine has the potential to interact with something, but there's no corresponding partner on adenine. Okay? And then we could do a very similar thing for cytosine. It's going to have the same basic 6-membered ring structure, but we're going to switch the character of the group, sort of occupying each position. So Cytosine has an NH2 group here, a ring nitrogen there. Sorry about the ugliness of some of those bonds. I really am not used to drawing six-membered rings on their sides. It's funny how that can make a difference. You have, again, an exocyclic amino group that's a hydrogen bond donor. You have a ring nitrogen that's a hydrogen bond acceptor, and then a carbonyl oxygen that's a hydrogen bond acceptor. And you can see that these are complementary to each other. So what I've shown you here are actually Watson-Crick base pairing between A and T, or U, and between G and C. Notice that the AT pairs have 2 hydrogen bonds, the GC pairs have 3 hydrogen bonds. You may have known that. If you've worked in a biology lab before where you have made primers for various things, for PCR experiments, you know that sequences that are rich in GC pairs are more stable than sequences that are not rich in GC pairs. That's just because GC pairs have more hydrogen bonding. What I'm showing you are the base pairing that can happen in a DNA double helix, though we haven't said anything yet about the structure, the remaining portions of the nucleotide and nucleoside. Let's see, one interesting feature, well, that's enough. You've got an exam coming up, so I'm being magnanimous and giving you the last 2 minutes of the class free. It's my gift to you. All right. Have a good day.